And that'll be the plan for today, okay? All right. So Gigi, you wanted 39, 29, 28. Boy, I'm on fire today. From 3.9. Oh, that's the page that is broken in the thing, huh? Where is that? There it is. All right. A kite 100 feet above the ground moves horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string have been let out? So that's kind of our situation, right? We have some kite, it's up in the air. There's the angle between the ground. What we're interested in is d theta dt, when I'm going to call that value r is equal to 200. That's what we're interested in. And we know d, let's call that side x is 8 feet per second. So far, so good? Okay. So if I take a look at this, what equation relates x, r, and theta? Well, theta is an angle, so probably not the Pythagorean theorem. I would say cosine, right? Oof, we're rough start this morning. That's true. That's fair.
Oh my goodness.
That's fair. Oh, and we're told the kite is 100 feet above the ground, right? Sorry about that. Forgot the 100 feet. Okay. Now, if we do this, if we differentiate here, we're going to be in a little bit of trouble, right? Because we're going to get a dx dt and a dr dt. And we don't know anything about dr dt. So we made a mistake because I forgot to write down the 100 feet above the ground to start with. So we shouldn't be picking cosine here. Or tangent, yeah, one or the other, doesn't really matter. So if you did, let's just look, tangent is opposite over adjacent, or cotangent would be adjacent over opposite. Either one should be fine. If you take a look at these, though, the right side looks a little bit more appealing for cotangent than tangent. But you could do either, would be okay. Okay, so let's say we do this one. If I differentiate both sides, what's the derivative of cotangent theta with respect to time? You mean negative cosecant squared d theta dt. And then what is the derivative of the other side? Okay. Because the 100 is a constant. You could if you wanted to, but it's like, you know, killing an ant with a sledgehammer, just like a little bit of overkill. Okay. So if I multiply both sides by like negative sine, or negative sine squared, I should say, there's the d theta dt by itself, right? Why negative sine squared? It's the same thing as dividing by cosecant squared, right? It's just multiplying by its reciprocal. Okay. So the 1 over 100, no problem. We got that. dx dt, we know that. It's 8. How do I do negative sine of theta squared? How do I calculate sine theta? The triangle, yeah. Because what do we know r is? 200 at the instant we're concerned for. So sine of theta is 100 over 200, or I'm just going to write 1/2. And then it's just clean up from there. And this would be what unit? Radians per second. Oh. Since it's talking about the change of an angle with respect to time. All angles in calculus are going to be measured in radians. And the rate for dx dt was in seconds, so I know that we should be in radians per second. Gigi, was that feel okay? Pierce.
Can I ask you to do a problem from an MCQ?
Yeah, of course you can.
Okay. Could you do 28?
Sure.
Because I think I know how you got the answer to, but I'm not entirely sure. So I just want to double check.
Yeah, no problem.
Yep.
Okay. So 28 reads, let f be the function with f of 0 equals 1 over pi squared and f of 2 equals 1 over pi squared. And the derivative given by f prime equals yada, yada, yada. How many values of x in the open interval 0, 2 satisfy the conclusion of the mean value theorem for the function of f on the closed interval 0, 2? So the conclusion for the mean value theorem states that there exists some c such that f of c, or f prime of c, should be equal to that. Okay. Should you know, like, your 3 value theorems by heart? Your intermediate value theorem, extreme value theorem, mean value theorem? Yes, you should know those by heart. So if I do that, well, f of b, a and b were just 0 and 2. So I get that average rate of change is just going to be 0. Because our a and b are just 0 and 2 here, right? So basically I'm looking for how many places is the derivative equal to 0. So if I apply the 0 product property, I can set each factor equal to 0. So I solve, I get -1, What's cosine inverse of 0? Pi over 2. And then also 3 pi over 2. If I divide both of those now by pi, I get 1/2 and 3 over 2. So how many of these satisfy our mean value theorem? 2. Why not 3? Yeah. -1 is not on my interval from 0 to 2, so it doesn't count. But the other 2 are, so those count. So
I don't think that's what you had written on your answer.
no.
Or at least like in your answer key, the 3 pi over 2 I think got cut out.
Oh.
Looking at it with Beck, we were really confused how you got 2 because we were like, yeah, because -1 is outside of that. You said it was -1/2, or you don't want to check it.
Maybe I made a mistake.
No, that's all right.
I make mistakes. It happens.
Can I just ask though, so for that first part, where you use the mean value theorem, is that is that just proving that you can? Are you just finding what you're gonna set that equation f prime equal to?
Correct.
Okay. So
Whatever that
you
number
would get,
is.
that's what you would.
Yeah. Now, I will tell you, in my experience looking at these AP questions, frequently that number is 0,
Oh, okay.
but it doesn't have to be. GG. That's okay.
When would you use the first and second?
To determine if the locations of local mins and maxes. That's what the first and second derivative tests do. They both accomplish the same thing. They're just, sometimes you may have only enough information to do one or the other, but oftentimes you'll have enough to do both, and then it's purely a matter of preference. Isabel.
So when you were finding like the cosine inverse of 0, like how did you?
So what I did is I say, okay, cosine theta equals 0. What are those thetas on the unit circle where cosine is 0? So on the unit circle, cosine is x. So I thought to myself, where is x equal to 0 on the unit circle? Well, it's when it's on the y-axis. So that's pi over 2 and 3 pi over 2. Does that feel okay?
Yeah.
Okay. GG.
And then
You set the second derivative equal to 0, and the solution to that will be your candidates for inflection points. And then you make a sine diagram, and you make sure that on either side of that potential inflection point, it goes from positive to negative or negative to positive. There has to be a sign change in the second derivative.
I'm kind of confused about the sine chart.
Okay?
Like, what do you plug it into?
So, say we have some second derivative. We set it equal to 0. And I get this. The answers are 2 and 4. So I'll make my sign diagram. So I'm going to pick a number that's less than 2, a number between 2 and 4, and then like a number bigger than 4. Does it matter what those numbers are? No, as long as they're inside the interval, it's going to be fine. And then I'm going to compute f double prime of those test values and just look at whether those numbers are positive or negative. I don't need the exact number. Oftentimes I'm just going to do it like, okay, positive part times negative part times positive part, and just do something like that in my head. But you could compute the entire number if you wanted to.
So, like, setting the first derivative equal to 0.
for critical values. Yes. But it's the same process. It's just one is with the first derivative and the other is with the second derivative. Now be careful, because there are critical values that are not the solution to the first derivative set equal to 0. It can also be where the first derivative fails to exist. So you have to be careful there. Isabel.
Can you do like number 1 and and then letter 2?
Oops, that's not what I wanted to do. Oh, do you just need D?
Yeah.
Okay. Average rate of change for G prime. Maybe I did that for G. I don't remember. Anyways, so I know G prime. We calculated that probably earlier, but that's going to be this, right? So my rate of change is going to be G prime of 3 minus G prime of 1 over 3 minus 1. That's my average rate of change. So if I do G prime of 3, that's going to be e to the 0. No, because this is f prime up here. So f of, well, that's going to be e to the f of 1 times f prime of 1 minus e to the f of 3 times f prime of 3. Oh, yeah, thank you. So 3s and 1s. Okay. Oh, yeah, well, it's fine. So f prime of 3 is 0. So anything times that is 0. And f prime of 1 is, well, we know f of 1 is 2. And then f prime of 1 is -4. So we should have 2e squared then as our answer.
I think I just forgot that it was asking about G and that F or something, and then I was looking at the graph.
This is a tough one because there's you have a graph of f that you have to use for a function for G, but it's not even the graph of f, it's the graph of f prime, it's
just a lot.
This is a tough one because there's a lot of you really have to understand what you're using and really be careful because it's easy to get kind of twisted and turned around inside of it. I started doing it, I probably was apt to make ready to make a mistake there, but I think that should be right. Do I have the wrong? Yeah, let's look at this then. Beck already found one mistake. Did I do the same mistake here? Yep, because look what I did. Look at this. Look at that. That's dumb. Look, g prime of x is f prime. That's What did I do? It's not even like close to being right, Mr. Kulik.
Okay, that's why I was so confused.
Yeah.
And I was doing that. I was so easy.
Didn't I send
I was
that,
like,
didn't I send that to you? I was like, is it the slope of, or is it f prime of 1 literally negative?
headshot for practice. I'm still in the car. Well, so.
Does she have the right answer?
What?
No? Okay, we're talking about something else.
I skipped breakfast yesterday, just started much more so now she's calling to ask me how the test was. Saying
Tell him that my teacher moved
You
it.
didn't have the option to take
You know?
it today, so that's on you. You could have taken it.
I choose not to get
Could have, I'm just saying.
I choose happiness. I choose happiness. Understanding.
Sure. Isabel.
What's up, dude? How you doing?
Can we also do a question where we're
Back
like,
there, man.
like see if it's an overestimate or an underestimate?
Yeah, if you could tell me what it was.
I got it.
Because I'll tell you the answer real quick. If the graph is concave down, you're going to have an overestimate. If it's concave up, you'll have an underestimate.
Wait, where did you say it again?
Well, if the graph is, oops, let's go back to this thing.
Oh, it's
So,
number 6.
so think about it this way, like concave down, if I draw a tangent line, it's always going to be an overestimate. If the graph is concave up and we draw a tangent line, oops, a tangent line, it's always going to be an underestimate. That's all I need.
Wait, that one on the left is kind of up, right?
Correct. Chi-Chi?
I'm gonna be asked to like draw graphs. Like that.
No. Okay.
I got it.
Okay.
Is it calculated one? 64 or 65?
On the multiple choice?
Yeah, I just need to make sure.
Yeah. Gigi, you're next, though.
Oh, my bad. I thought you were coming.
It's okay.
Actually, I have it like me first.
That's not me.
Let's grab one of these. Let's see here. Drop you in.
When I got to that point, I was just like,
Okay. So it's basically the same question each time, right? I can just do one of these and that's good enough. All right. So I'm going to, when I read this, there's two approaches I could take. I could take the second derivative of this and then look for set it equal to 0 and figure out where it's above and below the x-axis. Or I can leave it as is. I think I might try just leaving it as is. And then remember, our inflection points are boundaries between, well, let's think about it this way. Let me rephrase. The second derivative of f is the same as looking at the first derivative of f prime. Right? So if I'm talking about the second derivative of f, that's the same thing as looking at the first derivative of f prime. So I'm going to be using my first derivative test on f prime because that's what I'm given. Okay with that? So the places where the second derivative are going to be 0 is where f prime is got a maximum or minimum. The places where the second derivative is positive is going to be where f prime is increasing. And it'll be negative, the second derivative will be negative where f prime is decreasing. So if I look at f prime here, I'm going to be concerned about where it's increasing and decreasing at. And the boundary between those is always going to be a max or a min. Okay with that idea? So that's what I'm going to be looking at here. Because they tell me I'm looking between negative 1.5 and positive 1.5, I'm going to change my window on my calculator to represent that. And I don't know what the y's are going to be doing, but I suspect it's not going to be getting too terribly big because I know sine can be at most negative 1 and positive 1, and 1.5 squared plus 1 is not a massive number, so that's probably okay. And I overestimate, well, I need to check if I am in degree mode. The trig kids are doing degree stuff, so my calculator's never seems like it's in the right mode. Okay. So if I look at this, I see that f prime is increasing this little section here from negative 3 to whatever that is. Or I'm sorry, negative 1.5 to whatever that is. And then increasing on this section from negative whatever to positive whatever here, right? So immediately I know it's going to be either A or D, correct? I can just tell from looking at the picture, and actually have to find that point. Now, this spot right here, is that going to be negative 1.3 and change or negative 0.7 and change? It's going to be negative 1.3, right? Because that's 1 on, because that tick mark is negative 1. So at this point, I'm done. I know it's got to be A because that's the only one where that interval is increasing. That's got to be my concave up part. It's the only one that includes that part. I'm done. Does that feel okay? And I didn't have to do any real calculus on that. I just typed the derivative in my calculator and knew what to look for. You know what I'm saying? But that's a good one to look at, for sure. Because there's a couple of different ways to approach it. If I did the second derivative and set it equal to 0 and did a sign diagram or whatever, that's a lot of time. If I do this, it's ready to go. All I have to do is skip my calculator set and use my eyeballs. I think Gigi's next for questions if you were going to get me a question. Yeah. 4.3. Okay. And what number from 4.3? 40. Okay. Sure. All right. So, if I'm looking for the intervals of increasing and decreasing, what do I need to do first? I need the first derivative, right? The first derivative tells me where the graph is going to be increasing and decreasing just by looking at where it's positive or negative. So what's the first derivative of 5x to the 2/3 minus 2x to the 5/3?
What?
What did you just say?
That okay so far, Gigi? Okay. Now what I'm going to do is I'm going to set this equal to 0. because I'm interested in when this function is changing from negative to positive. It can only change from negative to positive at at one of these critical values, right? So I'll do that. How am I going to solve that for x? Okay, great. What am I factoring out? Obviously, 10/3 can come out. X to the negative 1/3. So that becomes 1. And what does this next piece become then? When we're factoring it out, we're dividing, right? So x to the 2/3 divided by x to the negative 1/3. I need to subtract the exponents. 2/3 minus a negative 1/3 is 3/3, or just 1. I can then apply the zero product property and set each of these equal to 0. This has no solution because it has an x in the denominator only. And then this one is 1. But hold on, because where else can we have a critical value at? Where the derivative is undefined, but the function was defined, right? So if I look at the original, the domain for this is all real numbers, right? Because we have positive exponents. It just, I can do cube roots of anything, positive or negative, not a big deal, right? If I look here, what's the domain here? That's an x in the denominator, right? What number gets me in trouble if I have it in the denominator? 0. So we also have a critical value of 0. Since the derivative was undefined at 0, but f was defined at 0. That's what you were saying earlier. I just want to make sure we discussed why. So I'm going to draw a sign diagram now. I'm going to pick some test values. So I'll pick a value bigger or less than 0, between 0 and 1, and then bigger than 1. Does it matter what those are? Not really. Actually, I think instead of 1/2, let's do 1/8. You'll see why in a second. All right, so if I plug this in, I'm going to plug this into the factored form of f prime. So when I plug negative 1 in, I get the cube root of a negative is negative, and 1 minus a negative 1 is positive, and a positive times a negative is negative. Okay with that? So I plug in here, that gives me a negative. I plug in here, that gives me a positive. So negative times positive is negative. I don't care what the number is. I just care about whether it's positive or negative. You know what I'm saying, Gigi? If you want to, you can plug them all the way in and get the actual number. But I'm going to pass when I'm doing it. I'm just going to if all I care about is positive and negative, that's all I'm going to calculate is positive or negative. So if I put the 1/8 in, if I was actually wanted a number out of that, it would be easy because I can do the cube root of 1/8 pretty easily, but I don't really care. All I care is that when I plug the 1/8 in, I get positives for both of those spots. And then if I plug the 2 in, I get positive, and then I get negative. So we are decreasing from negative infinity to 0, and then 1 to positive infinity, and we're increasing from 0 to 1. Part B says to find the local minimum and maximum values. Given what we've just constructed here, the first derivative test seems like the obvious choice because we have everything we need to just analyze our answer. So at 0, we're decreasing, and then we start increasing. That makes us a local minimum. And at positive 1, we go from increasing to decreasing. So we have a local maximum at x equals 1. But the problem asks for the local maximum minimum values. So I actually have to plug that x in to f to get the actual value. So when I plug 0 in, I get 0. And when I plug 1 in, I get 5 minus 2, so 3. So those are the actual answers we want. Is that okay? Plug it in to begin with.
Like you just look at the sign chart.
You have to look at the sign chart to tell if it's a max or min. They could both be this. They could be both 7, and one could be a local minimum, and the other could be a local maximum. You know, like the output of the value, because you could have like something that does this, and then something that does that, right? Where they have the same y value, but they are, one is a maximum and one is a minimum. So you can't tell by looking at just the number whether it's a max or min. You have to use the sign diagram to get that. Or you could do a second derivative test, but like, why? When you have everything you needed right there. Part C then says find the intervals of concavity and the inflection points. What do we need to use to do that? Second derivative. So I'm just going to differentiate this thing. So when I do that, I get 10/3 times negative 1/3 x to the negative 1/3 minus 1. I have minus 10/3 times 2/3 x to the 2/3 minus 1. Or what I have? Negative 10/9 x to the negative 4/3 minus 20/9 x to the negative 1/3. That all look okay so far, G. Gerino? Okay. Again, I'm going to now set that equal to 0. I'm going to solve this by factoring. I'm going to take out a greatest common factor of negative 10/9 x to the negative 4/3. So when I divide negative 1/3 by x to the negative 1/3 by x to the negative 4/3, subtract the exponents, negative 1/3 minus a negative 4/3 is positive 3/3, or just 1. I know, it's because I've lots of practice. You guys should write stuff down. Well, I've been a math teacher for like 15 years. So like, it looks really easy because it is really easy, even when it's this hard stuff. Even if I make mistakes, it's like it's pretty easy still.
Were you ever lost like this?
Yeah. Yeah, I've felt bad in math classes before where I'm like, I don't really know what's going on. It just takes. Listen. Let me be clear. I was no better of a student than you were at a comparable age. What separates me from you is 15 years of practice. It's like looking at a professional athlete and looking at a high school athlete. What separates them is like 15 years of practice, where you've kind of devoted your life to getting good at this one thing. So I should look a lot better than you guys look at doing this. That's okay. But that's the difference. I was no better at this at the equivalent age. In fact, I was probably worse than you guys are at an equivalent age. Just kept going. Okay. We're still not finished with this one. Gigi, do you have a question about what happened here?
Yeah. Don't you get from like 20
Oh, it should be a 2 on it, right? Thank you. See? Still making mistakes. Because it was 20 ninths. We factored out a 10 ninths. Right? So we'll do the same thing. We'll make our sign diagram. We'll pick a couple of test values. Oops, can't pick 0 though. Pick 1. If I do -1, I get negative times negative. That's going to make that positive. And then negative there. So 3 negatives. If I do +1, that's a negative, positive, positive. So that's going to be also negative. So there is no inflection point. And we are concave down from -infinity to -1/2, and then from -1/2 to +infinity. F or G double prime.
What I don't get about that, why couldn't you just write -infinity to positive?
Because the second derivative isn't negative at -1/2, it's 0. And 0 is neither concave up or concave down. It's like a flat straight line. So that's your reason. Yeah, I know.
Makes sense when you explain.
But it's like when I just want to write it all as one thing. I know, I get it. And when I put 1 in, I get negative, positive, and positive. So I have no inflection point. It's concave down basically everywhere but 1/2, or -1/2. And then is there part D? I'm going to skip sketching the graph after that. Okay. Okay. We probably need to do some of 1 or 4.5 now. So I'm going to cut you guys off on your questions. Feel free to come back and talk to me during community time. I get lonely. I have a really rowdy community time full of a bunch of knuckleheads. So if you come visit me, I'll be very happy to see you and talk to somebody about mathematics. So 4.5 is all about graphing without a calculator. That's kind of the skill that we're going to be practicing. So to do that, we're going to start by calculating all of these features for our graph, and then use those features to sketch a reasonable picture. So the features we're going to be concerned with is the domain. So I'm going to be interested in possible discontinuities. Those for sure have to make it into my graph. The intercepts, both x and y, so the places where we cross the x-axis or the y-axis. The symmetry, whether it's odd or even if it's periodic. the reason that's helpful for me is that I really only have to worry about half the graph if it's odd or if it's even. Or if it's periodic, I only have to worry about one section. I can just keep repeating over and over and over again. I'm going to worry about my asymptotes, vertical, horizontal, or slant. I won't be concerned about where the graph is increasing and decreasing. It's local mins and maxes. Then it's concavity and inflection points. So this stuff is like Algebra 2 stuff. Those last three are calculus pieces. So probably the part that's going to make this hard is remembering the stuff that we're supposed to remember. And this I'd almost like maybe overlap there, because we did asymptotes when we did limits. But I will probably default to our Algebra 2 rules because they're just a little bit quicker. All right. So let's look at this first function. Let's start with the domain. How do I calculate the domain for this? It's a rational function, right? Yeah, the denominator cannot equal 0. So I know x can't be plus or minus 1. So my domain should go from negative infinity to negative 1, and then negative 1 to positive 1, and then 1 to positive infinity. Oops, I meant to put a U there, not a comma. Look, still making mistakes. Even after 15 years. Yes?
So all this would be on the 5.
Yeah. So these last three sections still would be represented on the final. Okay. So now we'll do some intercepts. Let's do the y-intercept first. How do I calculate the y-intercept? You just plug 0 in for x, right? So there we have 0, 0 is a y-intercept. What do you also notice about this? It's an x-intercept also. How do you know it's an x-intercept also? Because the y-coordinate is 0, right? X-intercepts the y is 0, y-intercept the x is 0, right? So if I do my x-intercept next, how do I find the x-intercepts? I set y to 0 and then solve for x. What's the solution to that have to be? Just 0, right? Why can I see that just by inspection? For a fraction to equal 0, the numerator must equal 0. And the only way 2x squared can be 0 is if x is 0. Right? So just trying not to make more work for myself than I need. All right, so that's domain, that's intercepts. Let's look at the symmetry. Odd, even, neither. I know it's not periodic because it doesn't have a trig in it, right? Everybody's okay with that. So to tell if something is odd, even, or neither, we're going to do, oh, not f of negative 1. I meant f of negative x. So if I plug in negative x into all the places, and I simplify, I get this, which is just what we started with, right? That's f of x. So we know we're even. That's our definition for even, is if f of negative x is equal to f of x. Okay, what's next here? Asymptotes? Yep. Okay, what are our rules for asymptotes? For a rational function? Because f of negative x is equal to f of x. That's our definition for an even function, is if that relationship is true. So I just plug the negative x into my function and then simplified, and it's the same thing as it started with.
So it's not equal.
If it's negative f of x, it's odd. If it's something else, it's neither. What was...
The negative one and one.
Great. So we set the denominator equal to 0. So we have plus or minus 1. Good. How about a horizontal asymptote? No. I'm going to look at the degree of the numerator and compare it to the degree of the denominator. What are the three rules? Great, which is what we have here. Yeah. If, say, the top was 2x instead of 2x squared, what would the horizontal asymptote be if that were the case? 0. If the if the degree of the numerator is less than the degree of the denominator, it's always 0. What if the numerator was 2x cubed?
No horizontal asymptote.
It's not horizontal, but we do have a slant. How do we find that slant asymptote? Polynomial division, yes. And in this case, you couldn't use synthetic division because your denominator is not mnemonic. You'd have to do the long division.
Oh.
Mm-hmm. Leading coefficient divided by leading coefficient. Okay. And I'm going to do intervals of increasing, decreasing, and max and mins all in the same shot here, right? Because what are we going to use to do this? The first derivative. So we have to use the quotient rule here. So we have the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. Which simplifies down to just 4x over x squared minus 1 squared. Take a moment, see if you can see it. If you can't, there's no shame in writing it out, right? Sure, thanks. Absolutely should. Set the derivative equal to 0. What do we get for solutions? Should be able to do that in your head. 0. Are there any additional critical values from places where the derivative is undefined? Where would the derivative be undefined at? Rita? And? Yep. Are those count as critical values? No, why not? You're correct. They do not count as critical values, but why not? Because they were also undefined in F, right? They were not in the domain of the original function. So if they're not in the domain of the derivative, that's fine. So this is our only critical value. So let's see, 2 test values. How about -1 and +1? Those feel like good ones. If I plug -1 in, I get positive on top and positive on bottom, so that's positive. If I plug +1 in, I get negative on top and positive on bottom, so that's negative. So we have that 0, 0 is our local maximum. And we are increasing from -infinity to 0, and we're decreasing from 0 to +infinity. Of course. It's going to be a boring looking graph here, guys. You know why? There's like nothing going on here. Okay. The last thing we need is our concavity and inflection points, right? To do that, what do we need? Second derivative. So I have the derivative, or I have the bottom times the derivative of the top minus the top times derivative of, of the bottom. Be a little bit careful there because it's a gross looking kind of chain rule. So when I clean up that numerator, I get that. But I'm just going to set that equal to 0. And to get my solutions, I need to just do the quadratic formula on that fella right there. Now I do have to be a little bit careful here because I know my function can change concavity at these inflection points, but where else can it change concavity? at a discontinuity. How many discontinuities do I have in this function? 2, -1 and +1. So I also need to account for those when I do this. So we'll pick some test values here. All right, when I plug -5 in, what do we get here? We get positive in the denominator, and we have a negative times a positive, so that's just going to be negative overall. If I plug negative, well, the denominator is always going to be positive, right? Oh, except for at 0. But this one, denominator will be positive, negative here, and then the numerator will be negative. So that's 2 negatives over a positive. I plug 0 in, and I have negative times negative over negative. That's 3 negatives. I plug 2 in. That should be the same thing happening as -2. Oh, no, it won't be. Hold up the phone here, Mr. Kulik. So that'll be positive over there times negative over positive. So that part's going to be negative. And then 5, if I plug that in, should be negative times positive over positive. That should be negative also, I think.
Can I just ask you which equation you're plugging in?
To the second derivative. Ooh, oh no, guys. Hold on 1 second. I think I goofed that simplification there. Took the negative. Yeah, I did. Confound it. You guys are supposed to catch stuff like this. There. I know, I'm annoyed too. All right, let's try this one more time. So we have, we know we're going to have -1, we know we're going to have +1, and we know we have 2 plus √5 out there. 2 minus √5 is like, √5 is a little bit more than 2, right? Because √4 is exactly 2. So 2 minus √5 is going to be a little less than 0.
Yeah, oh my God. No, I get that. You can tell it.
Is that negative?
Yeah. I just had to make sure I had something smaller than 2 minus √5. All right, let's try this again now, you dum-dum. You know what? I don't like it when you call me dumb. Well, stop making dumb mistakes. That's fair, I guess. All right, so I have a negative times a positive over a positive, so that should be negative. And then I have negative times a positive over a positive, so that's negative. I have a negative times a negative times a negative, that's negative. And then I have 2, that's negative times a negative over a positive. And then that's, plug the 3 in, 9 minus 12, so that's negative, negative, positive, I think. Great googly moogly, Kulik. All right.
Can X still be a minimal?
Huh?
Can X still be a minimal? Because wasn't it like a discussion?
X still be X is a variable,
But,
right?
yeah. But didn't we say that -1 and 1?
Yeah, those were discontinuous asymptotes. So I have that, right? And I know we are increasing to 0 and then decreasing after 0. So it should look like that. There's my maximum at 0. And if I look, I am concave down on either side of that, in between -1 and 1, right? And then we are increasing from -infinity to 0, and we should be at -2. Really, is that, it's negative? That's, it's concave down. What is that going to look like? It should look like this.
How are you? Very sleepy.
How come this is... Why does that not look like that? That's what it should look like. Why are those not concave? Why is that not concave up right there? I don't know, I give up. Whatever. You get the point, right?
Yeah.
I've goofed some algebra somewhere. But that's what it should have ended up looking like.
Could this be like an F
It
would be a regular question.
I mean,
That's a lot.
yeah, look at the homework though. It's like there's like 6. I mean, look at what we had to do for that. It was like a nightmare, right? So it's not like that's a lot to do. On a test, I probably would not ask you to do an entire thing of this. I'd probably give you parts of it, ask you to do a couple of parts, and then to draw the result. You know, just to like, let's try to save some time here. Because I mean, I can't ask you to spend a half an hour on the exam doing one question. That's insane.
Can you go back over? So
I did.
we said earlier that -1 and 1 were like this continuity. You found that earlier in the question. And then on the sign chart, it went from negative to positive. So like realistically it's supposed to be a minimum, but because it's discontinuity, it's like we can't do that, right? So is that why it just like goes like to -infinity?
I am super interested.
So Because it goes from negative to positive on the sign chart.
For the second derivative or the first derivative? Because we have two sign charts.
The second derivative.
Okay, well, let's talk about concavity,
Oh,
right?
oh. First derivative is mid and last.
Yes.
Okay.
So that's just telling you it's an inflection point or something,
Okay.
right?
Okay.
You have a change in concavity there, which is in, which is something, but like,
Okay, there.
this was, I
Yeah.
wanted to answer your question,
Okay,
but I
yeah,
just
yeah.
kept getting lost in the
Yeah,
like.
I can see why.
What is that? It's in physics. I got the question 2 on physics. I did not do it. What'd you get? This is 19.
19.5?
I think yours is all.
Oh, you guys see that in 19 too?
I think you have two parts together, that helps, so it's like, where's the rest of hers?
19.5. How are you gonna say that?
You had the same thing for both
Yeah.
parts?
Maybe you're cheating off each other.
We definitely were.
Yeah.
No, I
I took it by myself.
Oh, where's your other half then? Do I have it slow?
Wait, 19.5 is great.
So 65.
There it is.
And I got 100.
I know. So how much?
35 point curve.
Very good, 90.
Oh, that's not how it works.
I could probably just tell you.
Yeah, how many? Yeah, could you know how much the curve was?
I think I did like 75% of the total points for max score.
Oh, so like.
Okay, so like, so
So
we got,
if this was out of like 39 points total right now, it just made it out of like 75%.
So, you can shut up.
Yikes. Well, you said I was
okay, so we got a 72 on curve, so it was at least 20.
Oh, you see, like, when I saw my grade go up, I was like, there's no way.
That's what I was thinking too, I was like, Mom.
What do you have?
Oh my god. That was my highest score.
Yeah.
Yeah.
Well, you guys are
I'm
working.
actually-
You guys are working very hard,
I'm
and
actually
like,
pretty worse than math than I am this time, so it's like a 94 in math.
This is how.
How do you have words?
Oh, really?
Dude, I want Garcia to put these stats.
That's three more points.
Oh, wow, this last page.
That's cool.
yeah. Hi.
Would you give us a question like this with, like, no calculator?
The no calculator, you can tell I can't do it. That's-
Which of the functions? F, G, and H.